Welcome. I will present the work that I carried out with Sandro Borasca. The paper deals with a method to describe the concepts and activities involved in the development of AI-intensive systems, that is, software systems in which AI plays a determinant role. The motivations of the work stem from the observation that the developers of AI-intensive systems are recognizing the need to organize development systematically and use engineered methods and tools. Therefore, a quest for software engineering for AI methods and tools has started. This quest could lead to failures and disappointments as happened for software engineering for regular software development a few decades ago. We should learn from experience and avoid repeating some of the mistakes made in the quest for software engineering in past years. To this end, a fundamental instrument is a set of concepts and annotation to deal with AI-intensive systems and the problems that characterize their development processes. In this paper, we propose a notation that was proposed for software engineering, and we adapt to describe AI-intensive systems as well. We demonstrate the usage of the notation by modeling some characteristics that are particularly relevant for AI-intensive systems. In what follows, we start with two descriptions. One concerns the environment and specifies the behavior of the considered fraction of the word. The other one concerns the requirements and specifies how the user would like the word to behave. Before proceeding, we need to introduce the entailment operator. In this example, we have that A entails B. This entailment creates states that from assuming A we can prove B. Accordingly, entailment is often called provability. We can express A and B at different levels of formality, ranging from informal text-based descriptions to complete formal specifications. In case of formal description, it is possible to prove whether the truth of B descends from the truth of A. Informal descriptions allow only for argumentations on whether the truth of B descends from the truth of A. In all interesting cases, E does not entail R. This equates to saying that the user requirements are not spontaneously satisfied in the environment. Clearly, no software would be required if E entailed R. When user requirements are not spontaneously satisfied in the environment, we try to satisfy them via a software system. That is, we place in the environment a hardware-software machine that interacts with the environment. The result of the interaction is a modified behavior of the environment that hopefully solves the user's problems. That is, achieves the user's goals. The elements of the notation proposed by Jackson are represented in this slide. We already introduced the environment and the requirements. The system is composed of a programmable platform that we call M and is readily available, and a program P that has to be developed specifically to satisfy R. The platform M can be a simple PC equipped with an operating system, as well as a much more complex platform involving, for instance, a set of machines and networking and middleware software, as well as specialized programming platform and libraries. Note that the real environment and the description E of the environment are not the same, unfortunately. Very often the knowledge of the environment is approximate or incomplete, which causes E to be a rather imprecise description of the real-life environment. As already mentioned, the interaction of the machine M and P with the environment E has to satisfy user requirements R. This can be written as shown here. E, P and M entails R. However, in general, we do not choose a programming platform and start programming right away based only on requirements. Instead, we usually devise an abstract machine S that can be defined in terms of its interaction with the environment. This machine S must satisfy R via its interaction with the environment. We therefore write that E and S entail R. The description S corresponds to the specification of the systems in terms of its I/O. Usually there are several different definitions of S that satisfy R. One of these is chosen, usually based on consideration concerning cost, development time and so on, and S is then implemented via M and P. Therefore, we can say that M and P entail S. AI-intensive systems, with special reference to those including a predominant machine learning component, can be described as the composition of the programmable platform M, a model MDL that supports artificial intelligence, that supplies artificial intelligence to the system, and the traditional software P in which MDL is embedded. And of course, we wish that the interaction of M, P, and MDL with E entail R. Now we can note a first difference between AI-intensive systems and the traditional software systems. In the latter, E describes all we need to know about the considered portion of the environment. That is, it is usually possible to describe the environment completely and accurately, at least in principle. So, in general, E describes satisfactorily how the considered piece of the world works. When we resort to AI-intensive systems, it is not so in general. For instance, when dealing with chess playing, we do not know how to play the perfect match. There is an hypothesis that who plays with whites is always able to win, whatever the player with blacks does. But we do not know how. We do not even know if this hypothesis is true. Similarly, when considering diagnosis of a disease based on tomography scan images, we have no rules or criteria to always get a correct diagnosis. The consequence is that we cannot devise an algorithm that always satisfies R. The lack of a complete and accurate description of the environment is particularly relevant because we can always express perfect requirements. For instance, we would like a chess playing system that always wins. And similarly, we would like a diagnostic system that always yields the correct diagnosis. If we adopt such a perfect requirement, we shall not be able to achieve the requirements based on an imperfect knowledge of E, because we shall not be able to conceive suitable specifications S. In most AI-intensive systems, data describes the environment. That is, we make up for the lack of knowledge concerning E via data that represent the observed behavior of the environment. We name this data DE, where E stands for environment. Usually, these datasets are very large, which is why we talk about big data. Regardless how large DE is, it represents just a part, often a small part, of the data that the environment is able to produce. As shown here, E can produce a set of data D tot, of which DE is just a subset. For instance, we have the records of many chess matches, but they are just a small fraction of the entire set of matches that could be played. When building an AI-intensive system, we derive a model MDL based on the available data. So, in the entitlement, we have D instead of E. SD is the description of the desired behavior of the AI-intensive system. Now the point is, how good is SD? Is the SD that we are able to build? In general, the system will handle most cases correctly. That is, requirements R are satisfied for a set of data ds that is much larger than D. This means that the system is able to correctly handle many situations that were not known during the training phase. Even though the system is able to handle most cases correctly, we cannot expect that the system handles all possible cases correctly. For instance, no AI-intensive system is able to win all possible chess matches, and no AI-intensive system is able to interpret any possible tomography scan image and always yield the correct diagnosis. This is represented in the diagram where data dtot that the environment can generate are a superset of the data ds that are currently handled by the system. When dealing with the evaluation of functional correctness of AI-intensive systems, we realize that there are some important differences with respect to traditional software. With traditional software, given the specification S, we need that P is implemented correctly. With AI-intensive systems, the fact that P is implemented correctly is not that relevant. Even a perfect implementation of P does not guarantee functional correctness, which depends mainly on MDL. With traditional software, we can modify P until R is satisfied for all test cases. With AI-intensive systems, we can hardly derive a MDL that behaves correctly for all cases in D. In general, AI-intensive systems do not satisfy functional requirements completely. Therefore, we need to quantify how much an AI-intensive system satisfies requirements, or the functional part of the requirements. To this end, we can split dtot into ds and df, such that the system behaves correctly, that is functionally correct, when dealing with ds, and behaves incorrectly when dealing with df. So, in principle, the sizes of ds and df can be used to evaluate the performance, that is the accuracy, of a given AI-intensive system. For instance, we can compute an accuracy indicator defined as the ratio between the number of successful cases and the total number of cases. In general, we cannot compute the size of ds and dtot exactly, but we can take samples and get an approximate value of the accuracy indicator. Another issue that is relevant for AI-intensive systems is the drift of accuracy in time. In fact, the environment often tends to modify its behavior in time, especially when the behavior is determined by people who operate in the environment. It is thus necessary to monitor the performance of AI-intensive systems and update the MDL when the performance drops below acceptable levels. Initially, the accuracy of the system can be computed based on DE. We can split DE into the data that are correctly handled, thus satisfying requirement R, and the data that are incorrectly handled. In this way, we can compute the accuracy of the system as we did earlier considering the dtot. Later on, we can compute accuracy on a regular basis, for instance every month, considering the performance of the system with the data handled in the considered month. When the accuracy decreases too much, we can recompute MDL, and to this end we can compose a suitable subset of all the data collected up to now. Which data should be used depends on the specific AI-intensive system. For instance, the most recent data could be considered more useful than older data. The proposed notation can be used also to represent some security issues that affect AI-intensive systems. A forced exploitation strategy is possible when the attacker knows MDL. In such case, the attacker can induce the environment to produce some data dx which cause a behavior that does not conform with R. An attacker may also pollute the data DE used to build MDL, so that MDL will fail when DX and similar data are used as the input of the system. Differences between traditional software and AI-intensive systems have been noted and described by several researchers and practitioners. However, sometimes the lack of a shared set of concepts and a common notation made discussions and descriptions rather imprecise and somewhat ambiguous. We proposed to use the notation introduced by Jackson to describe AI-intensive systems and their particularities. We showed that in this way it seems possible to write descriptions that help improve the comprehension of AI-intensive systems and the rigor of the discussion concerning their development, operation and maintenance. And that's all. Thanks for your attention.
Well, so hi, I'm Raghu Sangwan. I'm the chair of this session, and thank you for your presentation, Luigi. There are a couple of questions from so I'll read them in the order that they are listed in the chat. First one comes from Hans Martin. How do you determine what is acceptable performance of the AI system?
Well, okay. This is clearly very domain depending. So it depends on the specific system. For instance, we mentioned a couple of examples in the paper. One is a chess playing system, and another is a diagnostic system. So if you take a diagnostic system, probably the performance is acceptable if the system is as good as a human physician, an expert human physician, probably. But there is no general answer, so it is very, very application dependent.
Okay. Another question comes from Jane. She's asking, can you say something about how you estimate the size of DS versus DF for real-world problems? The estimates would be sampled based on existing model, which may not fully represent the real world.
Yes, okay, that's right, but that is what you have in some sense. So I suppose that if you have some data, it is the data that we called DE, so the data representing the environment in the paper, and you build the model based on that data, so that is the data that you use for training the model, then you know the performance of that model on that data, and so you can estimate the S and the F based on that performance. Or on a sample of that performance. Of course, going back to one of the previous papers, if you have in the image with snow, then you will be able to capture that behavior. If you do not have it, probably you will not be able to capture it. But that is a problem with our models, not with the formalism, unfortunately. So okay. It's a more general problem that we can manage.
Yeah. Okay, very good. So I have a question for you, Luigi. So first of all, thank you for a very nice talk. How do you envision carrying your formalism forward? You've heard lots of challenges that people have been expressing in the presentation of other papers. Typically non-determinism comes with new emergent behavior, new learning happening, and the system adapting to that new learning. How do you envision handling these kind of dynamic aspects that come with AI systems or AI-intensive systems?
Mm-hmm. Well, the idea is that some elements of the formalism could be seen as sort of time dependent, especially the environment. So we have written explicitly in the paper that the environment evolves in time, okay, and we need to continuously monitor the performance of the system and adapt to the changes. So that is probably one of the direction in which we could expand our notation in trying to apply it to problems where uncertainty and evolution are most prominent.
Okay, great. Well, thank you once again for a great presentation.
Thank you for your attention.